Welcome to the Deep Dive, where we take complex, fascinating subjects and really extract the crucial insights so you can get up to speed fast.
And today, we are immersing ourselves in the turbulent, brilliant, and, well, utterly unique life of a figure who completely redefined what it meant to be a genius, Richard Feynman.
Yeah, and he's so much more than just a Nobel Prize winner in physics, though. That certainly happened in 1965.
Oh, absolutely. Feynman was a phenomenon. He was the ultimate polymath, a master explainer, an expert safecracker, a professional-level bongo drummer, and one of the most influential theoretical physicists of the 20th century.
It's amazing. I saw that when historians of science took a poll in 1999, they ranked him the seventh greatest physicist in history.
Right. That places him right after names like Newton and Einstein. So that's the level we're talking about.
That context alone just tells you the scope of his impact. Our mission today is to go far beyond the textbook, synthesizing his massive scientific trajectory, from a self-taught childhood prodigy right through his essential world-changing roles.
In the Manhattan Project, the investigation into the Challenger disaster, we are going to unpack the foundational work that changed quantum theory forever.
And to do that, we've been through a comprehensive stack of sources covering his complex biography, his major scientific works like the revolutionary path and integral formulation, and those iconic Feynman diagrams.
And his enduring, sometimes, controversial public legacy.
And for you, the learner, we're framing this discussion around finding the pure aha moments in physics,
Yeah.
driven by a character who insisted on understanding the core conceptual truth.
The why.
Exactly, the why instead of merely memorizing formulas. This is a deep dive into fierce intelligence and uncompromising honesty in science.
Okay, let's unpack this.
So Richard Feynman was born in Far Rockaway, Queens, New York City in 1918. And his formative years immediately set him up for this intellectual nonconformity.
Yeah, you have these two contrasting yet complementary parental influences. His father, Melville, a sales manager who fundamentally encouraged challenging orthodox thinking.
And then his mother, Lucille, who instilled in him that quick wit and lifelong sense of humor he became so famous for.
What's crucial about Melville, his father, is that he didn't just teach Richard facts, he taught him how to think. He would challenge him with these intellectual games, encouraging him to see beyond the conventional labels of things.
And that influence showed up right away, didn't it, in his talent for independent theoretical analysis.
Immediately, you see that mechanical and theoretical aptitude merging in his early projects. Even as a kid, he had an experimental home laboratory.
The classic boy genius trope.
Right, but he took this real delight in repairing radios. And what makes this significant is how he approached the repairs. He would analyze the technical issues theoretically, just sit and think about it, and arrive at this structural understanding of the problem before he even touched the soldering iron.
The sources even mention he built an elaborate home burglar alarm system in grade school.
Just for the fun of it. And that ability to reduce a physical problem to its core theoretical components became the signature of his entire scientific career.
And that encouragement wasn't just for him. He was 9 years older than his sister, Joan Feynman, and became her most important intellectual mentor.
He really did, and this was despite their mother's traditional skepticism about women pursuing science. Richard actively encouraged Joan's interest in astronomy.
I love that story about him taking her out to see the aurora borealis right there in Far Rockaway, explaining the principles of the northern lights to her.
It's a fantastic reflection of his generosity with knowledge, and it paid off beautifully. Joan went on to become an internationally recognized astrophysicist who specialized in solar wind and its interaction with the Earth's magnetosphere.
So she helped explain the very thing he showed her as a kid.
Exactly. She helped explain the causes of the aurora borealis. His encouragement just overcame these significant cultural barriers.
Moving into his formal education, the title self-taught genius really sticks. I mean, by the age of 15, he hadn't just studied high school math.
No, he had actively accelerated his own learning, mastering trigonometry, advanced algebra, infinite series, analytic geometry, and both differential and integral calculus. He was teaching himself concepts that were, typically reserved for advanced university coursework.
This self-driven learning philosophy led to one of the most revealing details about his early thinking, his custom notation.
Right, his symbols. To avoid confusing mathematical functions with simple multiplication, he created his own unique symbols for things like sine or log. But the most telling one was his notation for the derivative.
The famous DDX problem. Why did he feel the need to change that?
He needed to remove the temptation of canceling out the d's in ddx. He fundamentally understood that the derivative is not a fraction. It's a single mathematical operator.
So he saw the notation itself as a potential trap.
He saw it as obscuring the underlying concept of a limit and a rate of change. So by inventing his own symbol for the derivative, he ensured that his focus remained purely on the concept of differentiation, not on, mechanical rote manipulation of symbols. That focus on conceptual truth was absolutely foundational for him.
It's also worth noting how conventional metrics they failed to capture this genius. His high school IQ test estimated his IQ at 125.
Which the biographer James Gleick famously called merely respectable.
Right. And later in life, Feynman himself joked that he couldn't join Mensa because his IQ was too low.
He was a lateral thinker, and standard tests often missed that. He applied to Columbia University for his undergraduate degree, but was rejected, a decision that's widely attributed to the existing quota for Jewish students at the time.
So he ended up at MIT.
Right, where he initially tried electrical engineering. He felt math was too abstract, before recognizing that physics offered the perfect blend of practical problems and deep theoretical challenge.
But the true, undeniable proof of his talent emerged when he applied to Princeton for graduate school.
He achieved an unprecedented perfect score on their physics entrance exam.
An absolutely perfect score.
And that perfect score came despite poor grades in history and English again. It just demonstrates a focused, asymmetric intellect. But this leads us to that critical, uncomfortable piece of institutional history.
The letter from the department head.
Yes. When Henry D. Smith, the head of Princeton's physics department, reviewed his application, he wrote to an associate expressing concern. He asked, "Is Feynman Jewish? We have no definite rule against Jews, but have to keep their proportion in our department reasonably small because of the difficulty of placing them."
That institutional anti-Semitism is just staggering. They were actively worried about his background, despite his, once-in-a-generation talent. So how did he overcome that?
Smith received reassurance that while Feynman was indeed Jewish, his physiognomy and manner show no trace of this characteristic. It's appalling. But this institutional acceptance, based on superficial compliance with racist criteria, meant they couldn't turn away a talent who had scored perfectly on their most crucial entrance exam. They were forced to accept his brilliance.
And here's where the science gets truly mind-bending. His PhD thesis, which he completed under John Archibald Wheeler, was titled The Principle of Least Action in Quantum Mechanics.
And it laid the foundational conceptual structure for the path integral formulation.
An incredible piece of work for a 23-year-old.
Oh, absolutely. His first seminar on the classical version of the theory, the Wheeler-Feynman absorber theory, was this star-studded event. You had Albert Einstein, Wolfgang Pauli, John von Neumann all in attendance.
What was their reaction?
Well, Pauli, the famously rigorous physicist, commented that the theory, which aimed to eliminate self-interaction and focus only on particle interaction, would be extremely difficult to quantize.
But Feynman found a way to quantize it, and in doing so, he provided the core aha moment of his early career.
The discovery that positrons could be interpreted as electrons moving backward in time.
That concept is so radical. To understand its elegance, you need to know the classical mechanics he was challenging.
Right. Traditionally, the principle of least action states that a particle travels between 2 points by taking the path that minimizes its action, a mathematical quantity related to energy in time. It assumes one single classical trajectory.
One path. And what did Feynman propose?
He proposed the path integral formulation. Instead of a single path, Feynman's new picture suggested that to go from point A to point B, a particle explores every single possible path simultaneously.
Even the crazy impractical ones.
Even the wildly impractical ones. And you have to sum the contributions of all those paths to get the correct quantum probability. It's often referred to as the sum over histories.
That completely upends our classical understanding of reality. And the backward-in-time positrons, where do they fit in?
That was the consequence of trying to incorporate the idea of antiparticles, like the positron, into this new quantum framework. Instead of introducing a complex new physical entity, he showed mathematically that a positron traveling forward in time is functionally equivalent to an electron traveling backward in time.
So it simplified everything.
It didn't just solve a theoretical problem, it radically simplified the description of particle interactions. It transformed this difficult complexity into a profound, almost symmetrical elegance.
And tucked right into the middle of this academic whirlwind is a really heartbreaking personal choice. One of the conditions of his Princeton fellowship was that he could not be married.
Mm-hmm.
But despite this regulation, and despite the tragic knowledge that his high school sweetheart, Arlene Greenbaum, was terminally ill with tuberculosis, he chose to marry her.
He knew she was expected to live only a couple of years. They married in a civil ceremony in June 1942. And due to the infectious nature of her illness, the wedding was profoundly restricted.
He could only kiss her on the cheek.
That's right. Immediately after, he took her to a sanitarium, Deborah Hospital, where he visited her on weekends, making that long trip while simultaneously juggling the beginning of the most intense, top-secret scientific effort in human history.
The Manhattan Project. Shortly after earning his Ph.D., Feynman was thrust into the highest levels of American science and military history. He was recruited by Robert R. Wilson, joining the theoretical division at Los Alamos.
Right, which was overseen by Hans Bethe. And he was immediately placed in a leadership role, quickly demonstrating that his practical engineering skills were just as sharp as his theoretical mind.
He and Bethe developed the Bethe-Feynman formula.
A key element used for calculating the energy yield of a fission bomb.
But his role wasn't just abstract physics. He was also the manager of the computation group.
This group consisted of human computers doing these tedious calculations. He streamlined their process, pioneering the use of IBM punched cards for complex calculations.
And in classic Feynman style, he also figured out how to program the IBM machine's clicks to output rhythmic musical patterns.
An early nod to his passion for drumming. But beyond computation, his most important, if maybe less heralded, contribution was in safety. He calculated neutron equations for the Los Alamos water boiler reactor.
But most critically, he was sent to Oak Ridge, Tennessee.
Yes, where enriched uranium was being produced and stored to devise safety procedures against criticality accidents, where too much uranium gathers in one place, especially if water is around to act as a moderator.
This highlights his commitment to accountability. He wasn't satisfied just writing some technical report.
Absolutely not. He saw a massive safety hazard. He insisted on lecturing the rank-and-file workers about the dangers, explaining the physics of why storing enriched uranium was fundamentally different and more volatile than storing unenriched material.
And he developed specific, non-negotiable safety recommendations.
He did, and he was authorized to tell the workers that Los Alamos could not be responsible for their safety otherwise if his proposals were ignored. That is scientific integrity actively demanding compliance from a bureaucracy.
It's during this time of intense pressure and secrecy that the famous jester persona really emerged, largely through his safe-cracking exploits.
You know, Los Alamos was arguably the most secure location in America, and Feynman found his amusement by cracking combination locks on colleagues' desks and secure filing cabinets.
He just viewed it as a puzzle.
A puzzle and a psychological observation. He discovered that many physicists, brilliant men preoccupied with subatomic structure, were incredibly predictable.
They used factory settings or ridiculously guessable combinations.
The most famous was Frederick de Hoffmann's secure cabinet, set to 271828.
Which are the first digits of E, the base of the natural logarithm.
Exactly. And he didn't just crack the safe, he would leave notes inside, sometimes an inside joke, sometimes a message simply proving he had accessed the secure documents.
He pulled a particularly memorable prank onto Hoffman.
He did, leaving several notes that spooked the colleague into believing a foreign spy had gained access to their most sensitive military research, which highlights the irony that surrounded Feynman at Los Alamos.
And the irony deepens when we consider the friend whose car he borrowed frequently for his trips to see Arline in Albuquerque.
Klaus Fuchs.
Klaus Fuchs.
Exactly. Fuchs was later identified as one of the most damaging Soviet spies of the entire project. When investigators asked Fuchs who else might be a spy, Fuchs mentioned Feynman's safe-cracking skills and his frequent unexplained trips.
So the FBI opened a file on him.
Despite Feynman holding a Q clearance, the highest level of security, the FBI compiled a bulky, suspicious file on him, believing his eccentric behavior might mask something deeper.
When the truth was, his deep secret was only his love for his dying wife.
And that personal devastation culminated in June 1945. Arlene died, and Feynman drove to Albuquerque and sat with her for hours. We know from his later memoir that he sealed a heartbreaking letter to her expressing his deep love, which was only opened after his own death many years later.
That kind of immense personal pressure, combined with the weight of the work, it had to manifest somewhere.
It did, and it culminated in his experience at the Trinity nuclear test. Here, the eccentricity met the sublime.
He claimed to be the only person to watch the explosion, Without the heavy dark glasses or welder's lenses everyone else was ordered to wear.
He did.
Why did he think he could get away with that?
Pure scientific reasoning. He was standing on a hill 20 miles away, inside a truck. He reasoned that the truck windshield would screen out the harmful ultraviolet radiation.
But he severely underestimated the sheer visual brightness.
Oh, completely. When the explosion went off, he saw the instantaneous blinding flash, forcing him to duck immediately to the floor of the truck. He saw a temporary purple splotch afterimage on the outside of the truck before the mushroom cloud started to rise. It was a risky act of scientific curiosity, even in the face of the ultimate physical event.
After the war, Feynman was briefly at the University of Wisconsin-Madison, though that didn't last. He then transitioned to Cornell University.
But the high expectations and the weight of the past immediately brought on a period of profound depression and professional stagnation following Arline's death.
It's a classic post-war psychological profile. He struggled to focus on major world-class research problems.
He felt immense pressure to follow up the bomb work, but he just couldn't find the motivation. The sources reveal he began tackling physics problems just for fun, purely for self-satisfaction.
Almost like a mental game to rebuild his confidence.
Precisely. And this leads to arguably the most famous anecdote about finding inspiration in the mundane.
The twirling dinner plate in the cafeteria.
Analyzing the physics of a twirling, nutating dinner plate tossed in the air, what seemed like a frivolous distraction, studying the wobbling and rotation of an everyday object, was actually crucial to his later Nobel Prize-winning work.
How so?
The equations he developed for the plate's rotation proved instrumental when he began thinking about the rotation and spin of subatomic particles. It just showed that sometimes the only way to break through a creative block is to stop trying so hard and focus on what genuinely sparks your curiosity.
Interestingly, his professional reputation didn't suffer at all during this time. He was receiving professorship offers from prestigious institutions like Princeton and the Institute for Advanced Study.
His perceived burnout was entirely internal. It was not noticed externally. And the world needed his mind desperately because the entire field of theoretical physics was facing a true crisis.
The problem of quantum electrodynamics, or QED.
Right. In the post-war era.
What exactly was the QED crisis?
In short, QED, the quantum theory of how light interacts with matter, photons, and electrons, it was mathematically unstable. When physicists tried to use perturbation theory to calculate high-order interactions, the formulas produced what were called infinite integrals. The math demanded that things like the electron's charge or mass should be infinite.
That sounds like the mathematical equivalent of dividing by zero in your theory.
It was completely nonsensical. It led Murray Gell-Mann to observe that theoreticians were in disgrace, and this confusion was palpable at the 1947 Shelter Island Conference, where experimental results, like Willis Lamb's discovery of the Lamb shift, had far surpassed the ability of the theoreticians to explain them.
So experiment was winning, and theory was failing.
Miserably.
So how did Feynman solve the problem?
He returned to his path integral formulation, using it to derive a renormalized relativistic equation for the Lamb shift. And the key was a mathematical process called renormalization.
Okay, could you quickly clarify renormalization for us?
Absolutely. The idea is brilliant in its simplicity. Instead of trying to calculate the theoretical mass and charge of the bare electron, which resulted in infinity, physicists realized they needed to treat the electron's mass and charge as the values you observe in the laboratory.
The empirical value.
The empirical values. You essentially introduce a mathematical cutoff term to absorb the infinities into those observed values. Feynman applied this process, and his relativistic result matched the non-relativistic version derived by Hans Bethe, proving the method was sound.
This successful application brought us to his most recognizable and enduring contribution, the Feynman diagrams.
He presented this work, titled Alternative Formulation of Quantum Electrodynamics, at the Pocono Conference in 1948, and the initial reception was hostile. Bewildering, even.
Luminaries like Paul Dirac and Niels Bohr were completely puzzled.
They were, because Feynman wasn't presenting equations, he was presenting pictures of lines and vertices.
So what are Feynman diagrams, conceptually?
They are the ultimate simplification. They're a powerful graphical language for quantum field theory. Each line, each arrow, each vertex in a diagram corresponds to a massive, complex mathematical expression needed to calculate the probability of a particle interaction.
So a single, simple picture of two electrons exchanging a photon might represent pages of calculus.
Exactly. They essentially turned the tedious, error-prone task of quantum calculation into a form of visual bookkeeping.
And yet, his co-Nobel winner, Julian Schwinger, famously dismissed them. He claimed they were just pedagogy, not physics.
That was the initial divide. Schwinger focused on extremely abstract, rigorous mathematical formalism. Feynman focused on physical intuition and ease of calculation. But the tide turned thanks to Freeman Dyson, who immediately recognized their utility.
Dyson helped to get his work published.
He did. He helped shepherd Feynman's ideas into publications starting in 1949. And suddenly, graduate students who had to perform these calculations, they flocked to the diagrams. They transformed quantum calculation from an arcane art into a practical skill.
Parallel to this scientific revolution, we see this persistent personal restlessness during his Cornell years.
A turbulent dating life, chasing women, a feeling of being overshadowed by Beth.
And this restlessness partially fueled his next move, a sabbatical in Brazil from 1949 to 1952.
This move was also deeply connected to the political climate. He felt stifled by the Cold War paranoia, the atmosphere of fear, and the intense FBI scrutiny he was still under, especially after Klaus Fucke's spying confession specifically referenced Feynman's safecracking. Brazil offered a change of scene.
While there, he fully embraced his non-scientific interests.
Oh, absolutely. He became deeply impressed with samba music, furthering his hobby of playing the bongo and conga drums. He even learned to play the frigidaire,
which is literally a percussion instrument based on a frying pan.
It is. But again, his scientific integrity shone through. He was teaching physics there, and he delivered this frank, powerful assessment of the Brazilian physics students. He noted their studying habits focused entirely on rote memorization of textbooks and formulas without any interest in context or application.
He noted they could pare back the definition of the Biot-Savart law, but they couldn't apply it to a practical problem or question why it worked.
Exactly. He criticized this focus on form over function, arguing they were not actually learning physics. This harsh yet honest critique was a precursor to his later famous attack on intellectual dishonesty in education.
In 1952, Richard Feynman settled at the California Institute of Technology, Caltech, which would remain his academic home for the rest of his life.
He was lured there by Robert Bacher, who recognized that Feynman needed a less constrained, less pressurized environment than he had at Cornell.
But while his professional setting stabilized, his personal life did not. Shortly after returning from Brazil, he married Mary Louise Bell.
And this second marriage, which lasted only until 1958, was tremendously tumultuous. It ended on the grounds of extreme cruelty.
The sources, particularly the FBI files, provide incredible detail here. They suggest the source of conflict was his inability to detach from abstract thought.
The court records and FBI reports confirm that his ex-wife testified that he was relentlessly obsessed with work and drumming. She claimed he constantly worked calculus problems in his head while driving or just sitting, and that when disturbed, he would fly into these violent rages, choking her, throwing objects, smashing furniture.
It speaks to a profound difficulty in balancing his ferocious intellectual life with emotional maturity.
It does, and his security file continued to complicate his life. After the 1957 Sputnik launch, the FBI interviewed a woman close to him, possibly Bell, who sent a written statement to J. Edgar Hoover calling Feynman a very definite security risk, immensely clever, dangerous, and worryingly unhampered by morals, ethics, or religion.
Wow. And despite all that, his scientific productivity never waned.
No. In 1958, the U.S. government still recognized his immense talent, sending him to the Atoms for Peace conference in Geneva. And it was there he met Gwyneth Howarth, a British au pair.
He initially hired Gwyneth as a live-in maid, paying her $20 a week.
And they eventually married in 1960. This third marriage proved far more stable, lasting until his death. They had 2 children, Carl and Michelle, and famously used his Nobel Prize money to buy a beach house in Baja, California.
During these Caltech years, his scientific output was just staggering. It spanned condensed matter, particle physics, gravity.
He provided a quantum mechanical explanation for the superfluidity of supercooled liquid helium, successfully showing that quantum behavior could be observed on a macroscopic scale, which was a huge conceptual leap.
He also fundamentally reshaped our understanding of the weak nuclear force. He worked with Murray Gell-Mann to develop the model of weak decay.
The VA theory. This was a major breakthrough because it solved the puzzle of parity violation. Parity is the concept of symmetry. If you look at a process in a mirror, the physics should still work the same way. But experiments showed the weak force violated this.
And the VA theory explained how.
It did. VA stands for vector minus axial, and it showed that the weak force only acts on left-handed particles and right-handed antiparticles. This discovery successfully described how fundamental particles decay.
But the relationship with Gilman was clearly one of intense scientific rivalry, wasn't it?
Oh, absolutely. Later, Feynman developed the Parton model to explain nucleon scattering, where he imagined the proton containing point-like constituents he called partons.
And Gell-Mann initially dismissed the name, calling them put-ons.
He did. But the experiments later proved that nucleons do contain point-like particles, quarks, and gluons, which complemented Gell-Mann's quark model.
And Feynman remained ahead of the curve. After the fifth quark was discovered in 1977, he immediately predicted the existence of the sixth quark, the top quark.
Just based on the internal consistency of his models, he even ventured into theoretical realms like quantum gravity. He looked at the photon, which has spin 1, and investigated the consequences of a free, massless field with spin 2.
And through that process, he derived the Einstein field equation of general relativity.
And in this work, he discovered these abstract mathematical entities he called ghosts.
Ghosts? Are these physical particles?
No, they are purely computational devices. In complex quantum field theories, you need these ghost terms to maintain gauge symmetry, which is necessary to keep the theory mathematically consistent. They appear in the intermediate calculation steps to cancel out unphysical effects that might otherwise break the math.
His contributions here solidified his reputation for having made influential contributions to all four fundamental interactions of nature.
Gravity, electromagnetism, and the strong and weak nuclear forces. It's an incredible legacy.
And beyond fundamental physics, he became the prophet of an entirely new field with his seminal 1959 lecture, There's Plenty of Room at the Bottom.
That lecture is widely credited as the intellectual birthplace of nanotechnology. He was discussing applied engineering and the potential for miniaturization. He theorized that if we could design tools at the microscopic level, it should be possible to arrange the atoms the way we want.
And he made that famous visionary suggestion of swallowing the doctor?
Yes, an idea he credited to his student, Albert Hibbs, referencing the possibility of creating tiny, swallowable surgical robots. To spur this kind of innovation, he publicly offered two $1,000 prizes for challenges in miniaturization. He really provided the initial spark for the field.
Moving forward to the 1980s, his visionary streak continued. He was one of the first scientists to conceive of the possibility of quantum computers.
And he spent summers working at Thinking Machines Corporation, where he helped them build parallel supercomputers. His intellectual curiosity was just boundless.
This incredible period of scientific productivity was also marked by his role as a legendary educator, resulting in the Feynman Lectures on Physics.
Right. Caltech asked him to spruce up the undergraduate physics curriculum in the early 1960s, and the result was the 3-volume series that remains a cornerstone of physics education globally.
How were the original lectures received by the students?
The reception was mixed. Feynman's own preface to the published volumes was actually quite pessimistic. Many freshmen found the material far too intimidating and advanced.
But faculty and older, more serious students found them inspirational.
Because they provided such a rare, deep, conceptual understanding of the subject matter, delivered with this unbridled enthusiasm.
This circles back to his fundamental teaching philosophy, a fierce opposition to rote learning and any method that prioritized form over function.
We see that critique brought home powerfully when he served on the California State Curriculum Commission in 1964. He launched an attack on the new math curriculum being introduced in schools. He specifically took issue with the elaborate notation for sets, the union and intersection symbols, arguing that teaching elementary students these abstract symbols was neither useful nor cogent.
He saw it as a massive waste of time teaching nomenclature instead of concepts.
Exactly. He argued that these symbols almost never appear in any writings in theoretical physics, in engineering, in business arithmetic. He saw the curriculum as prioritizing the appearance of mathematical sophistication over genuine, applicable knowledge.
And this brings us to what many consider his most profound piece of public advice on scientific integrity. His 1974 Caltech commencement address on cargo cult science.
This is perhaps the most actionable nugget of knowledge we can take from his life. He defined cargo cult science by referencing inhabitants of islands in the South Pacific after World War II, who built runways and control towers out of wood, mimicking military operations, hoping the cargo planes would return.
They had the form, but not the function.
Precisely. Feynman said science is rife with this. It has the appearance of rigorous scientific practice, but lacks utter honesty. He instructed the graduating class that the core principle of science is: the first principle is that you must not fool yourself, and you are the easiest person to fool.
So you have to be very careful about that.
That belief in relentless self-criticism, constantly testing your own assumptions against reality, was the engine of his entire career.
As we transition to his final public years, we have to address the controversial elements of his public persona, including allegations of sexism.
It's important context for his complex character. The sources confirm there were protests at Caltech in 1968 and again in 1972, objecting to his use of sexist stories about lady drivers and clueless women in his lectures.
And his famous 1985 memoir, Surely You're Joking, Mr. Feynman, amplified these controversial anecdotes, detailing meetings held in strip clubs and offering the controversial advice to ask women if they would sleep with them before buying them drinks.
That element of his personality, the complete disregard for social convention, produced both stunning genius and deeply problematic social behavior. However, it's also critical to note that the same anti-authoritarian streak could be used in good.
Like when he supported his colleague Jenna Joy Labelle.
Exactly. In 1977, he supported her in her Equal Employment Opportunity Commission suit against Caltech, helping her fight institutional resistance, and eventually received tenure in 1979. He stood up for her when the institution failed to do so.
As Feynman entered the final decade of his life, his fame expanded far beyond the scientific community, largely due to his massively successful memoir, Surely You're Joking, Mr. Feynman.
Published in 1985, it became an instant bestseller, cementing his image as the brilliant, witty, and profoundly eccentric scientist.
But that same memoir, which focused so heavily on storytelling, reignited his long-running tension with Murray Gell-Mann.
Right, his weak interaction co-worker. Gell-Mann felt that Feynman's account of the VA weak interaction work downplayed his own contributions,
The feud became so heated that Gell-Mann threatened to sue over the account.
forcing the publisher to insert a correction in later editions of the book. The conflict really boiled down to ego versus anecdote. Gell-Mann famously offered the cutting quote that Feynman spent a great deal of his effort generating anecdotes about himself,
Suggesting the public persona had overtaken the rigorous scientist.
It was a fascinating collision. But regardless of the rivalry, the anecdote generating had a profound and heroic real-world consequence shortly thereafter, solidifying his role as the public conscience of scientific integrity.
His crucial high-profile role on the Rogers Commission, investigating the 1986 Space Shuttle Challenger disaster.
He was initially very reluctant to join. He saw it as a political distraction, but his wife, Gwyneth, persuaded him, saying his unique perspective, his refusal to accept platitudes or hierarchy was essential, and she was right.
He immediately clashed with the commission chairman, William P. Rogers.
At one point, Rogers privately noted that Feynman was becoming a pain in the ass for asking difficult, technical questions.
But the moment that forever cemented his place in public memory happened during a televised hearing.
The O-rings.
He physically and visually demonstrated the catastrophic material weakness of the shuttle's O-rings.
It was a moment of pure, understandable scientific demonstration delivered to a national audience. He asked for a sample of the O-ring material, a synthetic rubber. He compressed the sample in a clamp, mimicking the pressure inside the rocket joint,
And dunked it in ice-cold water.
He immersed it in ice-cold water, mirroring the unusually cold temperatures on the Florida launch pad that morning.
And what did he show the world?
When he removed the clamp, the O-ring sample did not expand back to its original shape. It retained its compressed, non-resilient form. He visually proved that the O-ring material lost its elasticity and seal capabilities in cold temperatures.
Meaning the primary O-ring failed to seal the joint properly during ignition, leading to the leak that destroyed the shuttle.
It reduced a massive, complex engineering failure into a simple, undeniable physical truth. But his contribution went deeper. He discovered a profound systemic rot within NASA itself.
This is the most sobering takeaway. He conducted independent interviews with NASA's high-ranking managers.
And they confidently claimed the chance of catastrophic shuttle failure was extraordinarily remote, perhaps 1 in 100,000.
but when he spoke directly to NASA's own working engineers.
The people who actually understood the risk of unproven technologies, he discovered they estimated the probability of failure was closer to 1 in 200.
That is a terrifying chasm between management perception and engineering reality.
He was outraged, particularly because NASA had used that unrealistic 1 in 100,000 estimate to recruit people like Krista McAuliffe into the Teacher in Space program.
So he insisted on including his personal observations as a separate appendix to the official report.
Right. He threatened not to sign the final document unless it was included.
The appendix was included, and it contained what many consider his most famous public declaration.
He wrote the chilling, definitive conclusion. For a successful technology, reality must take precedence over public relations, for nature cannot be fooled. That single powerful sentence perfectly summarizes his lifelong pursuit of scientific rigor and honesty.
Throughout this period, the fundamental physics continued to bring formal recognition. The 1965 Nobel Prize in Physics, shared with Schwinger and Tominaga.
The Albert Einstein Award, the National Medal of Science. But despite the accolades, his anti-authoritarian streak remained. He was elected a member of the National Academy of Sciences, a high honor, but he ultimately resigned.
Julian Schwinger, his occasional rival, provided a wonderful summation of his character.
He called him an honest man, the outstanding intuitionist of our age, and a prime example of what may lie in store for anyone who dares follow the beat of a different drum.
The final curtain came after a long and difficult battle with cancer.
Liposarcoma, starting in 1978, and then Waldenstrom macroglobulinemia in 1986. He was hospitalized in February 1988, and when a ruptured duodenal ulcer led to kidney failure, he chose to refuse dialysis. He knew it wouldn't restore his quality of life.
There is a final sad detail about his lifelong dream of visiting the Tuvan Autonomous Soviet Socialist Republic.
Chronicled in the book Tuva or Bust, he spent decades trying to arrange this trip to Tuva, a remote republic in southern Siberia, fascinated by its culture and throat singing.
And the permission finally arrived.
Tragically, the authorization letter was delivered the day after he died in February 1988, an unfinished journey.
And in a final moment that perfectly captures his irreverent personality, his reported last words, referencing the extended coma that preceded his death, were, "This dying is boring."
We have covered an incredible scope of influence today. Richard Feynman not only revolutionized quantum theory with the path integral formulation and those iconic diagrams, but also pioneered the conceptual frameworks for fields like nanotechnology and quantum computing.
And most importantly, he provided a profound moral framework for science by upholding integrity in the highest offices of public life.
If we look for the core takeaways for you, the learner, the central lesson of Feynman's life is the necessity of balancing fierce, asymmetric intellect with a relentless, childlike curiosity.
He fundamentally taught us the importance of scientific honesty, the refusal to accept answers without conceptual understanding, and the absolute necessity of checking yourself first.
That intellectual fearlessness is a lesson applicable far beyond physics. It demands that we constantly ask the underlying why. But his story also reminds us of the tension between genius and the human condition.
Before we sign off, there is one final provocative thought about the legacy of knowledge. Feynman's friend and colleague, Danny Hillis, asked him in his final days why he wasn't sad about dying.
And Hillis quoted Feynman as replying, "When you get as old as I am, you start to realize that you've told most of the good stuff you know to other people anyway."
That sentiment raises an important question for you, the listener. What knowledge, what profound insight do you have left to share?
What unfinished intellectual or physical journeys, like Feynman's trip to Tuva, are left on your list? We encourage you to explore his work, especially his lecture volumes or his book, The Character of Physical Law.
And see how his refusal to accept authority or notation without deep personal understanding can change how you approach learning every single day. Thanks for joining us on this deep dive.
We'll see you next time.